Oh boy, welcome everybody back to the interval. It has been a very, very long time. Please give yourself a round of applause for actually showing up. This is our first kind of real live talk back here at the interval in a few years, and so thank you. And this has also been a talk that I've been talking with Creon about doing for a very, very long time. And unfortunately, the problem of space debris has not gotten better since we started talking about this. It's one of those issues like asteroid impacts, like climate change, that that we all face as a civilization, and I think it's one of those things that potentially we don't give the right due as we think on a civilizational scale.
Okay, I worked at NASA for decades, and for the last few years, I spent a lot of time on the space debris problem. I'll talk about why shortly. This is my hand, and this is an experiment that was run at the NASA Johnson Space Flight Center Space Debris Division's Hypervelocity Impact Facility. And what we see here is an aluminum plate that has been impacted at orbital velocities by a small steel BB. This is what can happen at those velocities with collisions with even small objects. This is a slightly larger experiment. This is a satellite mock-up. This is typical, small space vehicle, maybe a meter in length, maybe a little longer. And this was hypervelocity impact with a 1 centimeter, like marble-sized aluminum sphere moving at the relative velocity that your average space collision in Earth orbit might happen. And then on the right is the resulting fragments that they reassembled after the collision with the one marble-sized object. So small objects can make a big mess. I got drawn into this because when the Iridium satellite, which is a communications satellite, of which there are many in orbit, collided with a defunct Russian Cosmos satellite. I forget what its purpose was, but we don't really know what happened. In fact, the collision wasn't even predicted, interestingly enough, even with all the tracking of space objects that have been done. In 2009, they collided, and a big debris cloud was tracked. But as near as we can tell, this is probably what happened in the collision, was the Iridium just nicked this boom that was sticking out of the Cosmos. Cosmos is the left-hand one. And then this cloud of particles came about. This was a simulation done by Lawrence Livermore Labs trying to sort of retrodict what actually happened there. And this was thousands of fragments, thousands of trackable-sized fragments. And of course, every one of these fragments can potentially then collide with something else and make more fragments. Now, this fortunately has been relatively rare. The Gravity movie was showing a dramatization of something happening at the International Space Station, and this is a big concern. We really don't want anything even remotely like that. We don't even want anything to happen to the International Space Station. We don't even want a little tiny hole in it, although we'll talk more about that in a minute. It's truly an international project. In fact, one might argue that, one of the reasons the US and Russia don't go to war is because there's US and Russian astronauts up on the space station at all times. And it's sort of a soft power kind of detente diplomacy stabilization process politically. But technologically, it's an astonishing thing. There have been some debris strikes on the International Space Station that we know about. The Canadians have made big contributions to robotics on the space station. And so, unfortunately, one of their robots has been damaged by a debris strike. Again, this was probably only maybe a few millimeters in size, the object that made that hole. We don't know. There's this beautiful thing on the International Space Station called the cupola, which is this sort of picture window dome thing where it has no real purpose other than people looking through it and taking pictures through it and taking pictures of it. And they lie there and they look down at the Earth in this panoramic view. And it's a very beautiful thing. It's great that they made it. But what a lot of people don't know is on the outside of it, there are these shields that can be folded up. Actually, every time that they know that there's a substantial sized piece of debris, and by substantial, I mean anything we can track. And by anything we can track in low Earth orbit, I mean anything that's about 5 centimeters in size or bigger. When they know that there's something 5 centimeters in size or bigger that is has a conjunction probability of more than, I don't know, 1 in 10,000 with the space station. They close these shields and they actually get ready in the various human-capable vehicles that are on the space station to evacuate if a catastrophe happens. Here's some little tiny thing that hit one of the windows of the cupola. Didn't break it, but you know, all kinds of things up there. This is a solar array from the Hubble Space Telescope that was retrieved after 9 years in orbit and brought back to Earth. This is definitely debris strikes. I don't know the size of these solar cells we're looking at. They're probably at least like 5 by 10 centimeters, each of those things, maybe bigger. This drawing on the chalkboard, also shown here, is from the original paper in 1978 by Don Kessler and his associates. He was the man who essentially invented this field, or started thinking about the problem of space debris. And he started thinking about it in the 70s, and there had been no known space collisions at that time. He was just thinking, you know, what if we keep launching stuff into space and, you know, occasionally stuff blows up and occasionally pieces come off, and there's going to be a probability that things could collide over time and create more pieces. And
the idea is that if debris collisions produce more debris and produce more debris at a higher rate than it can be naturally removed or removed by humans, then you can end up with just an impassable cloud around the Earth, and you can just not be able to launch anything into space, maybe for thousands of years even. So the Kessler syndrome is the idea that there's this runaway chain reaction, and it just becomes, I don't want to say uninhabitable, but sort of space becomes unusable, at least near the Earth.
He made this graph showing predicted cumulative numbers of collisions based on different assumptions about how many objects were launched each year. Now, I should point out that it's now the 2020s, and we're launching many thousands of objects per year, not just 1,000 or so, like is shown here. I went, and the NASA Johnson Space Center has a whole debris office with like dozens of people in it who study this professionally for their whole careers, and they publish a newsletter, I think, quarterly. And one of the things the newsletter has, in addition to research, is it has discussions about various events that happen in orbit, and some are called collisions, and that's where they're pretty sure based on the tracking that something collided, and other types of events are called fragmentations. And fragmentations
can happen for many reasons. One reason is something can explode, like a fuel tank can get weakened if it's not empty and it's still pressurized and it's in orbit for a long time in and out of the sun. It can just crack and fragment and explode. Batteries can explode. Unexplained fragmentations could be collisions with objects that are too small to be tracked. And unexplained fragmentations could even be anti-satellite weapons, possibly. So what I did was I took this original figure from this original paper by Kessler from '78, and I looked in all these reports from the Johnson Space Center talking about the different events that have happened, collision events, fragmentation events, and I overlaid the cumulative number of events on Kessler's graphs. So in the solid orange circles are the collisions, and each time there's a collision, it goes up one more count. And these hollow orange circles are the collisions plus the unexplained fragmentation events. So what we see rather interestingly, and the upper right hollow orange circle is literally off the chart. I mean, it's a little bit off the chart. And what we see is that it's tracking his predictions rather well. As I said, JSC, you know, here we just see in 2020, they cataloged 5 breakup events. I don't know if they classify them as collisions or just breakups, fragmentations. I think these might have been all fragmentations. You can see some of these things that say satellite name are actually satellites, and some of them are third stages or tanks or covers and various large pieces of junk that are up there. Now, here's a graph that shows, this is again from JSC, it shows the total number of objects in space since the dawn of the space age, and they're classified by different types, as you can see. The most important one is the total objects, because when you're thinking about collisions, that's kind of what matters. And you'll see that there's those step functions in there, like the thing labeled 1 and 2 and 3. And one of those is the Iridium Cosmos collision I mentioned, that number 1, the thing that kind of drew me and a bunch of other people into this field. It was not the first collision, we don't think, but it was the first one that produced a lot of debris. And then 2 and 3 were anti-satellite tests, respectively Chinese and Russian. And as you may know, the US recently announced a unilateral ban on anti-satellite weapons testing. Hopefully the rest of the world will follow suit, because that's one of the most important things we could do, both for world stability and keeping the orbital environment safer in terms of debris. Remember I said we can track down to about 5 centimeters, but we have done experiments where we point high-powered radars. They're called beam park experiments, because you park the radar beam and you just point it at one spot. And as stuff goes in orbit, you get these radar reflections. So by taking a narrow, really high-power pencil radar beam and seeing what comes back, you can get range and cross-section and get statistics on what's up there. You can't survey the whole sky this way, but you can kind of get the fluxes and make assumptions that they're uniform, perhaps. And what we see here is a log-log plot. You can see that the number of objects of smaller size, if you go to 10 times smaller objects, there's like roughly 10 times as many objects. So it's a simple power law. There are 1,000 times as much flux of millimeter-sized objects as there is of, say, larger objects. This is just saying that there's a lot of small stuff up there that we're not tracking. And that small stuff, as we saw from the beginning, could be kind of dangerous. Interestingly enough, these are not distributed equally in space. There are certain orbital altitudes that are much more congested. You can see up about 850 kilometers. There's a lot of congestion. At these lower altitudes, though, it's kind of lucky. One nice thing about really low altitudes, like down below 500, is that stuff just doesn't stay up very long. Atmospheric drag slows it down, and as it slows it down, the orbit gets even lower, and then the atmospheric drag gets even higher, kind of gets exponentially higher as you go lower. And pretty soon, when you're down at 400 kilometers, you don't have long to live, no matter, unless you're very dense and heavy, like if we took that tungsten ball, it might live a long time. But most satellites or debris is going to live a very short time. What can we do to reduce this problem and ensure that we can continue going into space and don't face like a debris minefield that's impassable, full of satellites and nuts and bolts and other junk? Well, stop producing debris is the first thing. I should point out that the rules have gotten a lot more draconian, both the US rules and the UN rules. And like, it used to be that, you could like have a lens cap go flying off of your telescope and nobody cared, and you could have, explosive bolts send fragments everywhere when you were separating the rocket stage. And now all that stuff is not allowed at all, and all but the most pariah nations abide by these conventions. You have to go through a whole bunch of things to show that you're not going to be producing debris, that stuff's not going to fall off your spacecraft, that stuff's not going to explode. We have to stop doing anti-satellite weapons tests, because in a sense they're like designed to produce debris. And it's probably not a good idea. Another thing we can do is, we can just slow down launching stuff and wait for the atmosphere to clean stuff out. And that, as I said, works at the lower altitudes. But unfortunately, at the higher altitudes, 1,000 kilometers and above, that stuff's going to be up there for hundreds or even thousands of years. And when you get up into like GEO and the higher orbits, they're going to be there basically forever from our point of view, even from the long now's point of view, like millions of years, right? Another thing that helps us is the solar cycle. So the sun has like this 7-year cycle or 14-year cycle, depending on how you want to look at it. And it gets active and it gets inactive and it gets active and it gets inactive. And when it gets active, it puts out a lot more radiation at certain wavelengths. And they don't matter so much to us down here, hard to detect on the surface of the Earth. But in the very upper atmosphere, solar activity, particularly solar flares, those solar excursions make big changes in the extreme upper atmospheric density. They can change the temperature of the upper atmosphere and hence the density. They puff up the atmosphere of the Earth, and it gets way denser at like 200, 300, 400, 500 kilometers even above the surface of the Earth when the sun gets active. And that makes stuff get dragged down. much faster, because if there's more atmospheric density, it gets slowed down, and then it slows down more, and then it gets denser, lower atmosphere, and it burns up. This is the solar cycle, and the debris reentries kind of superposed with each other. So when the sun is active, the red curve, more debris reenters. So that's, you know, there's some cleaning that's going on naturally, but not enough. So another thing we do is we restrict the lifetime of satellites. And meaning, so we don't want a bunch of dead satellites up there. There are already too many, and we really don't want dead satellites up there. So what does that mean? Well, you can never ensure that a satellite won't die and just remain in orbit as basically a big piece of junk. But what you can do is you can say you have to dispose of it after a certain number of years if it's still alive. So you have to have an engine on it with enough propellant to take it and re-enter into the Earth's atmosphere, or at the very least, put it into an orbit that nobody cares about. So those are disposal options. Another thing you can do is just fly it very low to begin with, and then you know it's going to have a very short lifetime, even if it dies. That's what we do at Planet Labs mostly, is we build satellites, we launch them into relatively low orbits. They're only designed to last, say, 5 years, because after 5 years, the technology is presumably much better, and we don't really want them anymore, so we just have them at a low enough orbit that after about 5 years, they re-enter and burn up. But that's not always been the case. If you're building a billion-dollar satellite, you might want it to last a lot longer than 5 years, and therefore you have to be very careful and have some way to dispose of it. And unfortunately, the world's largest piece of space junk right now is a billion-dollar satellite called Envisat that the European Space Agency sent up there. It's about the size of a school bus, and it died. And it's totally dead. I mean, it's up there, and these very large dead objects are, in a sense, the biggest threat, because if something collides with them, they can make a huge mess. There's a lot of proposals also for going up and getting stuff out of orbit. That's called active debris removal. So the first thing that you can do to sort of avoid collisions, at least for active satellites, is have a traffic management system, kind of like we do with air traffic management. And you want the satellites you want everybody to know where all the satellites are, and you want everything in an orderly pattern so that collisions are very unlikely. This would be a typical distribution of satellites in a big constellation, like maybe Starlink or OneWeb or something like that. I mean, this is simplified, but a lot of satellites in a lot of different orbits. And it might look like a giant mess, and how could you how could you hope to not have a collision with a constellation this dense? But the issue is that if you look at it in a three-dimensional geometry, you can see that there's ways to kind of thread stuff through each other. You can imagine this thing sort of fully populated with these orange dots, like there could be thousands and thousands of them up there, and if they're all choreographed just right, they can sort of do a dance. And one way to understand the dance is to map it out in other coordinate systems, so that, like instead of latitude and longitude on the Earth, you can kind of map it out in these grids or in toruses where you're using different mathematical functions, and then they turn into these regular square patterns, and in a sense, every satellite is just sitting in a box. Now, when you put it back onto the 3 dimensions of the sphere of the Earth, it doesn't look like a box so much anymore. So here's the Starlink constellation, and we're mapping it out not in latitude and longitude, or not in altitude and inclination, or any of the standard orbital elements. And what we see here is a bunch of Starlink satellites, and the ones that are in their assigned orbits are these pale gray dots. And then the brightly colored ones are the ones that have been recently launched. So the ones that have recently been launched are the ones that are moving. And once they get into their assigned positions, they turn gray. Each different launch is a different color. And you can see as they get gray, they just drop onto this grid. And this means that even though they're all in orbit around the Earth, in this complicated dance, in this special coordinate system, they're just lying on a grid. The diamond-shaped ones are defunct. Some of those defunct ones, they're really defunct, like they have no control over them anymore. But the point is that you can see these gray ones on the right slowing down, and now they're locked into their position, and now we're going to watch these blue ones. They slow down and they lock into their position and turn gray. And you can see that they're slowly building up this grid. And then when you have this grid, if everybody stays in their box, once it's just a rigid grid and they're all up there and everybody stays in their little box, there's not going to be any collisions in that constellation. And so we could have boxes like that globally, for the entire world's satellites, actually. And we can have lots of satellites up there if everybody stays in their box. And of course, this is complicated by the fact that you've got debris objects streaming through here who don't know about the boxes, right? But it's a start. So what do we do about these debris objects? So we can do active debris removal. Everybody's got their favorite idea. Oh, we're going to build with a robot with claws, and it's going to grab stuff and then bring it back to Earth. Or we're going to this is an actual satellite servicing mission, but satellite servicing and debris removal are very similar. You have to get into proximity of another satellite. You have to grab it. You have to attach to it, and then you have to do something, either refuel it or bring it back to the atmosphere so it can burn up, or move it to some graveyard orbit. But this is very similar to what you'd have to do if you were trying to bring a dead satellite back. Now, the problem is, oftentimes debris objects and dead objects, they're tumbling. It makes it harder to get a hold of them. So, of course, people have said, oh, well, we'll just inflate like giant balloons, and we'll somehow stick it to a balloon, or everyone thinks they're very clever. Why don't you just send up a net? And the thing to remember about this is, these are objects in orbit, and if you do this, if you get something wrong, you end up just creating more debris. Like, you can imagine this net gets tangled up, and then now you've got an even worse problem, right? And now you've got an even bigger thing flying around there, or something accidentally, it gets tangled up and it hits something else. And also, by the way, all these kind of schemes like this, they also are like anti-satellite weapons in disguise, because I could just as well use this to go take your satellite and remove it, or to cover it up or turn it off, as I could to get out take a piece of space junk out of orbit. If there's something is tumbling, you have to. I don't know where people come up with these ideas, but I just collected as many as I could. We're going to catch it with harpoons. And then drag it away. Now, this was a European space mission that got pretty far along the planning phase, called E.D orbit. This thing on the right is that school bus-sized, gigantic ENVISAT dead environmental satellite, and then the thing on the left was fully all designed and ready to go. Well, it wasn't built yet, and it was going to grab the ENVISAT, which was not tumbling, I don't believe, and attach itself to the ENVISAT, and then just deboost the whole thing down into the atmosphere. And that got canceled, unfortunately. So that's ENVISAT is still up there. But they are actually this is going to launch in 2025. This is called Clear Space. The thing on the left is getting this medium-sized piece of junk that's known to be up there. And Europe is spending 86 million euros on this mission to bring back this one piece of junk. So you can imagine a scenario where you remove the N largest pieces of junk from orbit every year. And so the question is, since the largest pieces of junk are in a sense the biggest threat, because they'll produce the most additional junk if they get impacted, you might say, well, what effect would this have on the overall growth of the debris population if we removed the N largest pieces from orbit? So since we have good information about much of what's up there, and a lot of historical data, here we can see various growth scenarios for space debris. This is assuming no additional anti-satellite weapons tests, okay? But this says, if you just do business as usual, you get the thick black line that's going up and to the right, the highest one. And that's just using debris remediation techniques. And then if you use, if you add in ADRO2, which is active debris removal of the two largest objects, the two most dangerous objects per year, then you obviously get the dotted line, which is far less growth. And if you go to ADR5, that's the line that's almost flat going into the future. And that's if you remove the 5 worst offenders every year. So, and then the waviness of those lines is that solar cycle that I was talking about. So more stuff is going up there all the time, but more stuff is being cleaned out all the time, and you can balance it out. And then if you do a little active debris removal of just 5 objects per year, you can flatten this out. So that's pretty good news. Why not just send a giant laser up there and blast it and vaporize it? And it's like, yes, that was called Star Wars. That's called space weapons, and that is arguably I mean, if you have megawatt class lasers in space, oh, they're just up there to sell, mitigate debris. This is going to be a hard sell. Ming the Merciless was the only one who was capable of building such lasers, as I understand it. Yeah, ahead of his time, exactly. That's the thing. These things are also weapons. Some colleagues and I at NASA came up with a thing we called light force, which was a way to use relatively low power lasers to do space collision avoidance, not to blast things out of the sky or vaporize them. This was work that Will Marshall and I did back at NASA, and as well as a number of others whose names I shall mention later. And the idea was you use a ground-based laser hooked up to a moderate-sized telescope, shown here in the center, and let's say you're tracking a piece of debris that can't maneuver on its own, and you have a prediction that it's going to collide with another piece of debris that can't maneuver on its own. Now, these are the kind of, in a way, the worst problems, because first of all, there's arguably more debris than there is non-debris up there, and the second is that debris in general, debris can't maneuver, so there's no chance of somebody moving out of the way under their own power. So the question is, how do you prevent debris-debris collisions? And the idea is, if you shine this laser through this telescope on a piece of debris, you're not going to vaporize it or anything like that. You're going to put a little bit of what's called radiation pressure on it, the kind of thing that spins those little solar spinny things in those evacuated bulbs. And radiation pressure is a thing. You have to take the sun's radiation pressure into account when you're calculating the trajectory of a satellite in orbit. It's a slight perturbing force in addition to gravity and atmospheric drag. So radiation pressure is a thing, and it turns out that by using one of these industrial 10 kilowatt class lasers and a telescope of moderate aperture, like a university class telescope, like a 1 meter aperture telescope, using that laser and that telescope and some additional hardware, you can put enough light energy on a piece of debris that is equivalent to about what it would see in the sun, but you can put it either to slow it down in its orbit or to speed it up in its orbit if you point it in the right direction at the right time. And you can perturb the trajectory of that object. That's what's shown here on the upper right of this diagram, is like the unperturbed trajectory without the laser engagement and the perturbed trajectory with the laser engagement. You only impart a few millimeters per second of delta V with each of these engagements, but it turns out a few millimeters per second over the course of a few hours or days amounts to a lot of distance that you can perturb the end position of this object, and so you can actually avoid collisions this way. And the question is, how well does this actually work? What do the numbers actually say? How much is it going to cost? So we made this proposal. A whole bunch of organizations teamed up. Here's the picture of one of these lasers. It's about, I don't know how much these things cost. Some fraction of $1 million, I think, maybe less now. 10 kilowatts. That's about the size of a large fridge. Here's a 1 meter class telescope. That's also about $1 million, maybe a little less. And here's a high power adaptive optics system. That's another thing you need for this. And then if you combine this stuff together, this is showing like one piece of debris. It'll make passes over this laser, and sometimes you'll be able to engage it for a short time, and sometimes you'll be able to engage it for a long time, and maybe since it's orbiting the Earth like roughly every 90 minutes, most stuff in low Earth orbit is orbiting every 90 minutes, you would engage for maybe 16 illuminations over the course of 24 hours. Some of them longer, some of them shorter, and you could end up perturbing the position of this object by engaging with the laser and just giving it a gentle little pushes. You could perturb it enough that down the line, you've altered its trajectory by hundreds or even thousands of meters. That's shown here, the perturbed versus unperturbed trajectory. And this is with actual physics in the model, okay? It turns out our Australian colleagues then actually went and kind of did this. They at least demoed it. They had the laser, they had the telescope, and they did some demos of this. So we did experiments at the Starfire optical range. Here they are actually prototyping it on their optical bench. This is the high power adaptive optics thing. That's a technicality, but because of the atmosphere, you have to have some fancy corrective optics. And there's the Australian facility, Mount Stromlo, wonderful people. So this works. Last thing I'm going to talk about is a debris remediation scheme by George Sarver from NASA Ames. This is brilliant. He came up with this thing. Let's say you have like one of those swarms like you saw in the movie, the Gravity movie, where like there's like 1,000 nuts and bolts and little things all come in because maybe something fragmented and it's sort of a jet. Anyway, it was like, well, how could you possibly remove debris like that? Like, you're not going to, do that with harpoons, right? So his scheme is you launch a rocket, which is basically carrying a payload that's just a big tank of liquid carbon dioxide. Anyway, you launch this thing into a retrograde orbit, meaning the opposite orbit. If you have this cloud of debris particles coming, you launch this tank of CO2 so that it's going to intersect this cloud. And you time it so that it's going to intersect it on the night side of the Earth. And then, just in time, the CO2 tank vents all of its CO2, which goes from liquid phase quickly to gas, and then it turns into crystals, dry ice crystals. It's on the night side of the Earth. So these dry ice crystals just sit there. Imagine like this long contrail of dry ice crystals that's been precision laid out so that the debris cloud is going to pass right through it. And then the debris cloud, and then the rocket kind of re-enters itself using its own jets of CO2, leaves this debris cloud contrail right in the path of the oncoming debris. And the oncoming debris comes and it just gets ablated by this cloud of dry ice crystals. All the nuts and bolts and everything slowed down, burned up. And then what happens? 20 minutes later, the Earth rotates and all this is in the day side, and the crystals just sublime and instantly dissipate because they turn back into gas, which expands immediately. So I thought that's a brilliant scheme. Maybe we'll do that someday. Real practical ones. I think I'm going to end it there. Thanks very much.
So thank you. I really appreciate that you actually showed a hopeful view of space debris in this talk, which is very rare that we get to see. And when I visited you guys in South America, this is maybe a couple of your places, your offices ago, but it was kind of stunning to me after going to a NASA launch and then showing up at Planet. There was, you guys were tracking at that time hundreds of satellites from one screen in South America, and then going to NASA where there are like hundreds of people tracking one thing. But that kind of difference that's happening in the now that we have so many private efforts, how do they? You mentioned this coordination thing. How is the coordination happening both between international secret things of military and less secret things and the private world?
Yeah, that was a lot of stuff in there. So let's talk about first.
Is there one database? How does it work?
There's essentially one database. No, even that's complicated. But everybody knows. It's kind of like asking, is there one search engine? You know what I mean? Like, there's several of them, and most professionals know how to use multiple ones, and that's not a huge issue. And there's ways to combine them to get higher accuracy, fusion and all that stuff. I want to give some credit to NASA and these kind of places. Look, I love Planet Labs, but when we have hundreds of satellites controlled by one person, these are like basically simple little webcams in space with some radios on board. When NASA has hundreds of people controlling something, it's like the space station or a Mars rover or something like this. It's like a whole other level of complexity and risk. I mean, if one of our satellites goes out, it's no huge deal. If one of those Mars rovers goes out, it's like hundreds of careers and billions of dollars. So there's a reason that we do things differently. I have the highest respect for NASA in many ways, in spite of my snarky comments earlier.
And one of the things that I don't think we talked about, you kind of showed it at the beginning, but like, what are the velocities that we are talking about? Like you showed
average low Earth orbit collision velocity is many kilometers per second.
In miles per hour?
Tens of thousands of miles. I mean, it's like 10 times faster than a rifle bullet in general. So hypervelocity, like hypersonic.
And you mentioned one of those unpredicted collisions that happened with the Canada arm. And a few of those, like how many of those are we now seeing per year?
Well, again, to see it, we have to either have astronauts up there noticing that there's a hole where there wasn't one before, or we have to see some event with a radar on Earth, and that means it's got to have big fragments. So we're only seeing right now, as I said, fragmentations like from 0 to 3 or 4 a year, maybe 5, but we don't really know. This micro fragmentations could be happening more frequently.
And we have a question from the internets, and we're going to grab some questions here from the audience next as well. Is there a current curve that's heading us towards a Kessler syndrome? That if left alone, where would we be?
If left alone, like if we stopped
I
launching
mean, you
stuff?
showed a curve that was going up that we were hoping to flatten
Right.
of space debris. At what point does that curve hit Kessler?
Oh, well, don't forget that curve. When I plotted those points on top of Kessler's thing, I mean, we were talking about, over the course of many decades, an aggregate of like 12 collisions. So we're not in like any sort of horrible situation right now. You'd have to extrapolate those curves much farther to have a real impenetrable wall of space debris in orbit around the Earth. The curves which showed those growth scenarios that were actually coming from the NASA debris office that show a more linear growth scenario, that's, I think, more like what's in our near future. And the question is, are we just going to let it get worse and worse, or are we going to flatten it out? It's not that much work to flatten it out. Is it going to go nonlinear? It depends on it depends on your time scale. Like almost any curve is linear if you zoom in far enough.
Yes. All right. Do we have any questions? Short questions? Charles. Let me repeat that just since we don't have a mic out there. So given what's up there right now, what is the chances of a big, nasty collision? We've already had 2 that were maybe planned or were like the Chinese one and the Russian one, but something on the order of the gravity kind of collision.
This is very hard because this is kind of one of these low probability, high impact events. It's like a Poisson process. So, you know, it's like, I don't know how to answer that. The gravity thing was exaggerated and it wouldn't really go like that. But like, what's the probability of a big object smashing into the space station? That's very low because we know where the big objects are and we know where the space station is and we're going to move the space station out of the way, okay? But that Iridium Cosmos collision that kind of dragged me into this, which produced thousands of fragments, many of which are re-entered by now. But yeah, I think we can expect to see every few years something like that, maybe bigger. It's a Poisson process. So sometimes a lot of them come and then there's a big gap.
Fair enough. Other questions? Paulo? So the question is, could you use any of these systems, like the laser system you mentioned, effectively to push something into a correlated orbit? And if it did happen, would anybody be able to detect that it was happening?
I think the answer is it would be very hard and you could detect it. And it doesn't really matter because how would you even know if someone was nudging this debris or if it was just that was how it was headed? I mean, what I'm saying is that you'd see that there's a collision probability and it's getting worse as time goes on, and so you'd make a maneuver. And if you're just trying to make debris collide with other debris, that's just terrorism. That's like you're not taking out anyone's asset there, you're just making a mess.
Right. Other questions? Are the graphs including the particles that are too small to be tracked? Is that what you're asking? Gotcha. So they could have probabilities, but we're not tracking them. Is that what you're asking? Yeah.
Some of the graphs showed particles that are smaller than the ones that are tracked because we do know something about what's up there of even a very small size. Like that's one of the reasons they brought back those panels from the Hubble Space Telescope. It's like, well, those things have been up there for 9 years, and you know they're going to have 9 years worth of bombardment, and then you can go look and see how many holes of a given size there are, and you can at least know roughly the statistics of what's up there and how dangerous it is. Obviously, you're not tracking every single sand grain or BB in orbit, not yet. We could make radars that might be able to do that. But so it's kind of a mixed bag. We know something about the statistics and distributions of the smaller objects and something about how dangerous they are, but we certainly don't know where everyone is at all times.
All right, so I'm going to wrap this up, and we're going to stay here, and people can ask more questions, but I want to kind of bring this back to that original kind of question of threat models that we all have to hold in our heads these days. Is this question of, where does this fit in your head in the world of something like climate change or an asteroid impact or some other kind of existential threat? Like, how do you put this into your...
Yeah, well, okay. I'll end on a controversial note. Climate change is not an existential threat. It's not an existential threat to the planet or even to humans. It could be a serious problem that could set our civilization back, maybe irrevocably back even. I mean, so could the Kessler syndrome. It could lock us here on Earth. There are similarities. I mean, and then neither is the Kessler syndrome an existential threat. Like, the worst it's going to do is, keep us from going into space for 1,000 years. Okay, we lasted a long time without ever going into space. Okay, but I'd like to, and asteroid impacts, that's too far. That's too different. I think there's great similarities and great differences between the space debris problem and the climate problem. And I'd like to focus, they both seem similar because they're like global environmental problems, and it's a coordination problem because you have to try and get everybody to do something, and it's going to be it's going to be somewhat expensive in the case of space debris and horrifically expensive in the case of carbon emissions, at least, that part of climate change, to mitigate in the standard stupid ways that they want to mitigate it. I should be careful what I say, but there's similar problems in this way. They're up in the sky, they're like involving the whole Earth, but they're also very different problems, climate change and space debris. I mean, space debris is a simple problem. First of all, there's no question about, are humans contributing to it or not? Like, okay. Secondly, and how much are they contributing?
There's no non-anthropogenic problem. Yeah.
Right, exactly. There's no, right. It's all anthropogenic space debris, pretty much. And then there's the issue of, like, how good are the models? Well, like, people argue about these climate models all the time. It's like so hard. I'd venture it's almost impossible. It's not my field, but it's like, I've done fluid dynamics and I've done chemistry, and I can tell you we can't even do tiny little airplanes and simple molecules very accurately. And the idea we're going to model the whole planet with the sun and the magnetosphere and the biosphere and the oceans and make predictions down to a fraction of a degree Celsius over the course of decades, I find that preposterous. And contrast that with space debris. It's like Newtonian orbits and collision statistics. There's really not much to argue about, right? It's like the models are pretty simple. You can run them on a laptop.
Well, I like coming out of here thinking that space debris is less of a problem than I went going in. So thank you for that.